In this exercise, we are going to obtain two numerical approximations of two numbers, this one and this one, using Taylor polynomials, here of degree 3, here of degree 2. All right. Okay. Well, let's consider the first. We need a function, right? Well, clearly, the function here, one function suggests itself is this one, right? And which is equal to x minus 1/2, by the way. And we need a point A around which this number is close to this point, right? So the closest point to this number for which the square root is easy to evaluate is the point 1, because the square root of 1, okay, the square root of 1 is just 1. So this is f1 is equal to 1, okay? Fine. So we need 3 derivatives for the polynomial and the fourth one for the remainder to estimate the error. All right, so we need to calculate derivatives. So this is minus 1/2 x minus 3/2, right? Second derivative is 3 over 4 x minus 5/2. Third derivative is minus 15 over 8 x minus 7/2, and the fourth derivative is at x is, this is plus 7 times 15 is 105, and then the denominator is 16 here, and then we have x2 minus 9/2 here. Right, we won't need more. From this, and given that we are approximating around the point 1, we have to evaluate these derivatives at 1. So we have the first, which is minus 1/2, the second, which is 3/4, the third, which is minus 15 over 8, and well, the fourth, we're going to need the fourth for the remainder. So first, let's compute the Taylor polynomial. The Taylor polynomial of degree 3, right, around the point 1, will be 1 minus 1/2 x minus 1 plus 3/4 x minus 1 squared minus 15 over 8 x minus 1 cubed. All right. So we have this polynomial, and now with the polynomial, sorry, there is, the denominators are not right, because I have to divide here by half. So it's, remember, this coefficient is the second derivative divided by 2 factorial, so it's 8 what I have to put here, and in this case is the third derivative over 6, which is 3 factorial. So it's 48 what I have to put in the denominator. Yes, 48. Okay, and we can simplify, because 15 is 3.5, and 48 is 16, right? Yeah, 16 times 3. So the 3 goes away. So this is actually 5 divided by 16. So minus 5 divided by 16. Okay, so this is the final form of the polynomial that we're going to use to evaluate this this number. If we evaluate the polynomial at the point 1.1, well, all these x minus 1s become 0.1. So this is 0.1, this is 10 to the minus 2, then this is 10 to the minus 3. So clearly the terms are in decreasing powers of 10. So at the end, if we evaluate that, the approximation we obtain for this number is 0.953437. Okay. All right, now we need to evaluate the remainder. Okay, for this we have this, right? And we need an intermediate point, C. Intermediate point is between 1 and x, which is going to be 1.1, right? So is 1 plus theta times x minus 1, which is the same as 1 minus theta plus theta times x, right? Okay, theta is some arbitrary number between 0 and 1. All right. Okay, so the expression of the remainder is remainder of order 4 around the point 1 of x is equal to this divided by 4 factorial. So when we divide 105 over 16 by 4 factorial, which is 24, and simplify factors, what we're going to obtain is 35 over 128. Right? And then we have the 9th power of 1 over the square root of 1 plus theta x minus 1. Okay, this to the 9th power, right? And then this is multiplied by x minus 1 to the power 4. Okay, sorry, this is not the remainder 4. This is what we call the remainder 3, because this is the remainder of the third order polynomial, right? Okay, now we need to, this is the difference between the function and the polynomial. So what we have to estimate now is what is the absolute value of this, what an upper bound to the absolute value of this. Well, clearly x minus 1 is positive, right? This is actually 0.1, okay, because x is going to be 1.1, okay? So this is positive. So 1 over the square root of 1 plus theta x minus 1 is smaller than just 1, because the denominator is larger than 1, right? It's 1 plus something, okay? So it's larger than 1, so this is smaller than 1. So it's very easy. The approximation that we can make here is the absolute value of the remainder is smaller than 35 over 128. This the upper bound of this is 1, and then we have the absolute value of x minus 1 to the 4th, which is, given that x minus 1 is 0.1, this is 10 to the minus 4. Okay, so this, an estimation of this is just 2.7 times 10 to the minus 5, which means that the error is affecting the fifth decimal position, so this one here. So the approximation we're giving of this number is just 0.9534, and the 3 is dubious because it may contain an error, but at least these 4 figures are correct. And if we calculate the exact value with a calculator, the exact value is 0.95 346258, etc. Right? You can see that the 4 figures are exact. Okay, so with this approximation we obtain 4 exact figures of this quantity here, which is pretty good. The second number we need to estimate is the cubic root of 28. All right. For that, we're going to use the function the cubic root of x. And we need for a one number that is close enough to 28 so that the local approximation makes sense to approximate the cubic root of 28. But at the same time, the cubic root must be easy to calculate, and that number is 27, because the cubic root of 27 is equal to 3. That is f27, all right? Okay, so we need derivatives of this. Remember, this is just x to 1/3. So if we calculate the first derivative, this is equal to 1/3 x2 minus 2/3. The second derivative is minus 2, 3 by 3 is 9, x2 minus 5/3, and the third derivative, which we need for the remainder, is 5 times 2 is 10, 10 divided by 3 by 9 is 27, x to the minus 1/3. Okay? So with these numbers, we can easily calculate what is f prime of 27. The cubic root of 27 is 3, so this is 1 over 3 times 3 squared, which is 1 over 27. The second derivative is equal to minus 2 over 9, and then times 3 to the 5. Let me check what this is. This is 2000. This is minus 2 over 2187. Okay, so if we have this 3 as the function and these values for the first and second derivative, then the second order polynomial at 27 is simply 3 plus 1 over 27 times x minus 27 minus this divided by 2 factorial, so 1 over 2187 times x minus 27 squared. All right. So if we want to evaluate what is the polynomial at 28, which is our approximation to, the cubic root of 28, this is going to be, well, 28 minus 27 is 1. So this is 3 plus this minus 2187, and that is numerically 3.03 657979. All right. Okay, this is the approximation that the polynomial provides. Now we need the remainder. For the remainder, we have the third derivative. The remainder of order 2 around 27, okay, is the third derivative divided by 6, right? Because it's 3 factorial, and that is 6 is 3 times 2. 10 divided by 2 is 5, so it's 5 times 27 times 3, so it's 5 times 81, divided by 81, sorry. And then we have, of course, x minus 27 to the power 3. As a factor, as a multiplicative factor, then we have to divide by this, evaluate it at an intermediate point. So that is the 8th power of the cubic root of 27 plus theta x minus 27. There you go. And theta is an unknown number between 0 and 1. So this number is between 27 and 28. Okay, this is very easy to find an upper bound of, because the cubic root of 27 plus theta x minus 27 x minus 27, this is equal to, this is larger to the cubic root of 27, because this, whatever this is, well, this is actually 1, so this is positive. This is positive. Even if we ignore what is the value of theta, we know that theta is positive, and this number is 3. So 1 over this is this cubic root, okay, is smaller than 1/3. So 1/3 is an upper bound to the cubic root, the 1 over the cubic root that you have here. So we have to raise this to the 8th power, and then we have our upper bound. So our upper bound is this. Is 5 over 81 times 3 to the 8th times x minus 27 in absolute value cube. Okay, so this number here is, well, this number is 1, of course, and this number here is 531,441, right, which is approximately 0.9408 times 10 to the minus 5, which is approximately 10 to the minus 4. It's almost 10 to the minus 4. Okay, so that means that if we go here, the fourth figure here can be tainted by the error. So this figure here. So we're sure about these four figures, but this one may change a little. And actually, if we calculate what is the exact value of the cubic root of 28 with a calculator, what we get is 3.0365889, etc. So you see, these first four figures are correct. By chance, the next one is also correct, right? It could be tainted depending on because the error is affecting the fourth figure, almost the fourth figure, right? But it's not. So we have at least these four figures correctly, and in this particular case, we also have the next one as well, right? But at least we are sure about these four. Okay, so this is how you use this kind of things for approximations.